who's a researcher at Inria, and he's going to start off, well, he's going to give both of the talks, and he's going to start off with one on language support for asynchrony, and it's titled Tail Modulo Async Await. So please take it away.
Thank you. Let me try to put that. Okay, maybe not. All right. Okay, my slides are not connected. Yes. They were connected before. Okay, very good. All right. So this work comes from sort of an interesting place. Is that Ludovic, my co-author, really likes concurrent languages, and I like functional languages. And at some point we go together and say, why doesn't this work? And a master's student later, this is the result. And so, I mean, you're a functional programmer, and the best friend of the functional programmer is recursion. And so if you do a normal recursion, as you know, you will have some stack, and some stack, and some stack, and some more stack. And at some point, you might have an issue if it grows too large. And naturally, the nice solution to that, you tweak a little bit your code. For instance, you move to an accumulator style implementation, and then you use tail calls instead of normal call, which means that the recursive call is the last call, the last operation of the function. And in that case, we don't have any more stack issues because tail call will not have accumulate stack frames. And so we get a different calling convention, which is a tail call, and it worked nicely. And then, when you have a recursive function where all the calls are tail, you can do more things, and you can do, this time, a compiler transformation, not just runtime support. And you can derecursify your function, and then you have a nice loop, and then performance people are very happy because it goes fast. Okay. So that's nice. Now, let's say I want to write asynchronous code. And so here I want to write this read all function. So for this, the purpose of this talk, I'm going to assume that I have a let async, which just means that the function is asynchronous. It's going to run in some green thread and return a feature. And so you can see the signature at the top, this read all function, an integer, and it's going to read n files and return the concatenation of the content as a future. And since I have asynchronous I/O, I will need to do some async, some await. And so here I await for a file to be read, and then I concatenate by awaiting on the recursive call. Is that clear enough? Yes. All right. So again, I would have lots of stack trace and so on and so forth. Well, actually, not completely. So again, I can move to an accumulator style thing, where I have some accumulator that is going to contain the strings that I accumulate. And then I do the concatenation here, and so on and so forth. Probably should be the reverse, but oh, you get the idea. And if I do that, then I don't have so much problem on my stack, but I have another problem now, which is that I'm going to do a chain of await where I read all at this point, and then I await on a future at this position here, and then I await on the next one, and so on and so forth until I reach my final value. And so I'm going to have I don't have a long chain on the stack anymore, but I do have a long chain in my futures, which means I still have exactly the same problem as before. And so our contribution in this talk is a new notion of tail asynchronous calls that I will try to detail, which is sort of an alternative calling convention, just as Haskell calls, and a code transformation, which I will call destiny passing style. I will explain why later. And an extension to tail modulo cons, which was recently introduced in OCaml, semantics, some proofs, we'll see, and a partial implementation, and we will have lots of discussion on that towards the end. All right, so the first key idea is to use promises instead of future. So a future usually you introduce with async, and then you access it with await, and a promise gives you on top of that a write once pointer that allows you to fill the future. And obviously you should not try to access this pointer several times. It's only write, it's write only and write once. And so concretely, I have my future. If I took the previous example, I had a riddle. It points to a box, and this box I will be able to use an operation, which is called fill, and we put the value in the box and be done with it. And so if I go back to my previous code example, I will transform it in several steps. The first step will be to add what we call a destiny, a new argument D, and the destiny is the future result, the future position of the result. Where should the result go eventually? Or the destiny of the computation, if you want. So this idea of destiny, it's been used quite a while in concurrent languages. If you want to look, there's a very nice paper called Forward to a Promising Future, with lots of puns, which introduces this notion of destiny more formally. And so we add this destiny argument, and then we pass it along to the recursive call, because we're interested in the accumulator, and it will contain it will be put in the destiny. I have put some holes here, so let's see how we can fill that. When we reach the bottom, then we fill the destiny with the accumulator. Okay. And then we need to start somewhere. And so we now have a notion of promise creation, which gives us both a future and a destiny. The future is read-only when the computation is ready, and the destiny is write-only and write once. So this notion is present in quite a few future and promise library. In OCaml library, we tend to call it a resolver. In other various libraries, it has different names. And now with this transformation, my read-all function doesn't return anything anymore. It's just a unit, because at the end it will perform a side effect to fill the destiny. It still can do some await here and there. And interestingly, I can return the future directly. Actually, it's missing something here. It should be an async here additionally. So we can launch the computation and give the future directly, and when the computation is finished, the future will be readable for the consumer. Okay, so I've done this code transformation, and now I have recursive function that doesn't return anything, and the call here is tail. So, okay, I'm happy. If I do that, I will have a small call stack, and my chain of future is short as well. And so I've gained in both the stack and the future. Nice. Okay. So this worked well. You can implement that pretty easily. It's a simple code transformation that is very similar to the tail recursive transformation. Now, what about constructor? I told you at the beginning we would look at tail modulo constructor, and this is the real purpose of this talk, in fact. The previous one was just a bonus. So, we recently got in OCaml tail modulo cons, and it's an old technique from the scheme and Lisp days, which is that we can write a function that is recursive and whose last recursive call is under a constructor. And in this case, we can use tail modulo cons, which is to turn into a DPS, destination passing style, where we give a destination, and the destination eventually will be written and will correspond to the cons of the thing. And then we make a pointer to the whole. Okay, let me do that again, sorry. We first allocate the cons before doing the recursive call. We get a pointer to the whole, the part of the list that is not yet written, and we pass that pointer to the rest of the computation. And the rest of the computation will eventually write the value inside this whole. And so that's exactly here. We have a cons here which is allocated with a whole. We get the destination, and we pass the destination here. Okay? And so this is taken directly from the tail modulo cons paper. And so this destiny passing style, you might notice some similarity, right? It's like you have this mutable variable that is that you can put your result in. It is write only. It should be written once, and so on and so forth. What about functions on trees? So here we were very careful. We only have one recursive call, and so this only recursive call can be turned into a tail call. But if I have a recursive function on trees, then this map here will be tail modulo cons, but I cannot have two functions that are two calls that are tail modulo cons at the same time. That doesn't make sense. I'm in a sequential context. What am I going to do? Which one am I going to use first, and so on. So that doesn't really work. But in an asynchronous context, I don't really care. I can do both calls at the same time. And so if I consider this asynchronous function, which is still a map on trees, if I get a node, I call v, so it is an asynchronous function like last time, and I can await on both map and launch both map concurrently, and eventually I should get a result. And so the idea of this work is basically to take functions that look like this and do exactly the same as tail modulo cons, which is to allocate the cons first, launch all recursive functions, and figure out how to pass things so that at the end we get our value back. Okay. So the key idea here is basically the destiny is half a promise and half a destination. It's sort of a mix of these two ideas. And so a destiny is a whole where we are going to place the value to be computed. But unlike the destination that we used previously, we can have multiple write once pointer in the structure at the same time. And the value is ready, which means the computation is fulfilled when there are no more holes. So if I take this function on the left, which was a map on trees from before, we are going to turn it on the thing on the right. So don't try to read it too much now. I'm going to come back to it later. The thing that is interesting is that we have some functions that work on destinies, and then we have a forking call at the end, which is going to call the recursive function by doing a fork. All right, so what's those destiny things? So here is a sort of API for destiny. It's actually not a real API, so those are not real ML type because it doesn't type. And it shouldn't, it's internal to the compiler, so it doesn't need to type. So we have a type. A destiny of an alpha destiny is a hole in a value, which will be filled by a value of type alpha. It must be used linearly, because otherwise we would try to write several times in the same hole. We can create a new destiny, and it gives you, as before, two views: the destiny, which is write only, and the future, which is read only. And the future will only be ready later. And finally, we can refine a destiny. We take a hole, we take a value with some more holes. Well, sorry, we take a destiny, which is a pointer. We take a value with some more holes. We put the value inside the destiny, and we obtain more destinies pointing to the inner holes. Okay, let's look at that graphically. So we have this pointer pointing to a big value with two destiny, D1 and D2, with some holes. We have a context here, which is basically a value, a cons. Refine will put this inside D1 by returning two new destiny, D3 and D4, which point to the new holes. And so we can propagate the computation like that by keeping track of all the holes in the value. But at some point we got to end. And so we have this value here, which we want to put in the destiny D. And we notice that this value does not have any more holes, and this one only have one hole. And so when we put the value in the destiny, then we lift a flag saying, this is it, the value is ready. Because we know that once we reach 0, there are no more holes available. Remember, the destiny should be used linearly, and so the number of holes can never grow again. We can never reintroduce holes in the value. Okay, so let's look at this, the code that is generated now. We're going to start from here, and at the we're going to allocate a new destiny. So it gives us a future and the top level of the value with a destiny inside, the destiny D. It has one hole and it is not ready. We start our computation. So for example, we're going through the node, and so we are going to allocate the node with some values, and the destiny D here is not available anymore. We have refined the destiny, but we have two new destinies, DL and DR, that correspond to the holes that are available right now. And we can keep going. So for example, I can use DI and fit it with a leaf. I update my counter as I go on, and so on, and so on, and so on. And now I've reached 0, and so now I know that my value is ready. So I lift my flag, and I update the future to point to the value. All right, so that's pretty much it. So we've defined the semantic for destinies and forking calls on paper. There is a work in progress proof of simulation. Unfortunately, the internship was a bit too short, and so we didn't got time to exactly finish those, but we're working on it right now. And we can implement those destinies in unsafe OCaml, and it works fine. So it's a nice proof of concept. The problem right now is that we sort of have a dilemma. I cannot experiment with this just in source OCaml because I cannot express forking calls. So if you look here, I have this fork call function, and I cannot explain to OCaml, please stop caring about the stack for this call. That's not an operation that is available, and it probably shouldn't be. So in source OCaml, I cannot write that. But on the other hand, in the OCaml IR directly, there is no notion of asynchrony. So I cannot really explain all this to OCaml either. Because in OCaml, async are effects and they're user side. So there is sort of a question, how do we actually put all this in OCaml? And where exactly should it sit in the compiler stack? So I see Pierre doing some back and forth. So yes, so that's pretty much it. And if you have any question or remarks or propositions, I'm very welcome to it.
Yeah, I have a question at the very beginning.
Okay.
So in a way, I was wondering, why would I want this? And then my suspicion went along the lines, aren't you just, and it's not just, but isn't this mainly creating an opportunity to make explicit in the high-level language how to do task parallelism?
Yes, and so sort of, yes. But also the real reason is to do this. It's basically to have function over branching structure that are stackless.
Well, if I look at a purely functional semantics, I say, oh, there's two recursive calls. Surely I can do them independently. So shouldn't my compiler be doing this for me?
Well, no, it is.
Well, yeah, this is precisely the point. So in a way, this would give the programmer the ability to make this explicit.
Yeah.
So do you have in mind that, or is one of the motivations of your work that you want to take an ordinary functional program and then translate it into something like this as an intermediate code so that you get more transparency about what is going on when it comes to performance or not so much performance? Or is it a general observation that for recursive data structures with more than one branch, this is something that you would love to have?
I think it's more of the like that. Like it's just like if you have a branching structure, and you're okay with having the computation being concurrent, then you don't need to pay the price of the stack, basically. You do need to be limited by the stack, should I say. That's really the observation here. Now, could it be transformed into more of a task-based thingy? I mean, it is task-based, clearly. I think it's a good idea as well. I'm not sure, but I think so as well. As I said, at the end, it's not exactly figured out how to really make advantage of this idea. So, maybe?
And if I may put it another question. So you said, oh, in OCaml we can't do this because we can't fork a new thread. So if I think about Haskell, then they have this par thingy,
Yes.
which in principle you could abuse, maybe?
Maybe. I think it would be the same so in Haskell it would be inside the compiler, definitely, as well.
So OCaml doesn't have something like a par construct?
Not really.
Not really, yeah, sounds ominous.
No, but the async and await in OCaml are going to be library side.
Ah, okay.
Which means I do not have access to them inside the compiler.
I see.
So, yeah.
Thank you.
Yeah, I'm curious about how exactly you define the semantics for this, because I look, and to me, it's like a really strong parallel with the process calculus, where you have like your holes and your destinies are like channels, and I feel like if you model this as processes, you could infer this automatically, do this in a much more general way, probably, because this is like a very simple transformation over processes. Yeah?
Probably. The slightly tricky thing, well, tricky, I don't know. The point of this is that you can do that in the middle of a general purpose language that has a traditional style semantics. Mm-hmm. And so I do not know if we have process-based semantics or semantics that look like process calculus for, you know.
I don't know exactly how
Yeah.
async works inside of OCaml either. So.
But so yes, and I mean the formalization we have is sort of a bit like that, really, and the proof is by simulation, so it's pretty much like that. So a little bit, yes. Yes, we are early, but we can.
So maybe I'm missing something, but regarding the integration with OCaml,
Yeah.
since like all the concurrency future stuff is going to be provided as libraries,
Yeah.
couldn't you just for any function where you want to apply this transformation, pass it, I don't know, like a module that contains the functions that you want to insert, and then arguably, I mean, probably this function needs to work properly, but then you just insert them and pass a correct module. And
I mean, the problem is that the transformation has to be inside lambda. And I do not know how to expose that kind of interface from lambda.
yeah, like an annotation in the tree, an attribute as an attribute to the definition.
Ah, that's true. I could do that.
You already have to do this when you do tail modulo cons, right? So
I'm not sure I would get that merged. I'm
Okay,
pretty sure I would not get that merged. But,
would that work in principle?
Hmm?
Could that work in principle?
Probably.
Okay.
Probably, yeah. But it would not be usable by people. Because it would need a fork compiler.
I mean, okay. Okay, thanks.
Okay, let's thank the speaker.